Steve's got a super short bio now. Steve Martin retired in January of 2021 as the top surveyor for the East Bay Municipal Utility District. EBUD, EMUD,
EB Mud.
EB Mud. After 34 years split between EB Mud, the County of San Diego, and the City of San Diego, he now resides in Las Vegas, thankfully for us, and continues to be active in the land surveying community, which you would have seen GPS on benchmarks for the last all summer long. Steve running around and hitting all the monuments. He even just did one yesterday, right? In Pahrump, I think, or Saturday, one of the two. Yeah. So
I've been at it for 2 years now.
I know it's been amazing. On top of that, he was helped with Caltrans and CLSA with the LSIT training study stuff. So Steve's passion would be a lot of these speaking engagements. He speaks at the conferences as well. So if you come to any of the Western state conferences, you might get to see Steve. So I loved taking the time to have you on tonight, Steve. And GPS, basic GPS was kind of the topic for tonight, which I think anybody watching today will learn, and anybody watching a year from now is going to learn. So I love it. Thank you for always taking your time, Mr. Steve.
Well, thank you, Trent.
Of course.
Yeah, good evening, everybody. I have to admit, I was a little surprised when Trent asked me to be on because, I'm no Gary Kent or
whatever
in any of the other long list of luminaries that have been on here. But as Trent briefly mentioned, I have been involved in, LS exam prep programs, probably since the mid 90s. And, at the conferences, doing GPS and geodesy. I'm leaving out the geodesy part tonight. At the last CLSA NOWS conference, we had a packed room and hour and a half, and it was really too much material for an hour and a half. So at an hour here, hopefully we're going to wrap up in an hour. We'll see. And so just GPS basics, and we'll get started then. Yeah, I was fortunate early in my career to be invited to a sit on a Caltrans LS exam prep program, probably, within 2 years of getting my LSIT. And then the organizer of that, Vance Brashears at Caltrans, he asked me to stay on and do the GPS and geodesy part because I had, I had worked on the HPGN survey in California, and I was doing the geodetic control networks at the county when I worked there. And this is probably why Trent asked me on. I told him I was teaching a couple of classes online. And he said, well, when can I get you on? So just the last 2 months, I taught NC Survey 035 map projections, and then NC Survey 030 GNSS techniques here, all online. And so the students are moving on to control surveying using GNSS coming up next with Kevin Maxwell. And then he's going to do 045 also. And then they're going to jump back to 25 survey data adjustments, J satellite, and 20 GNSS leveling, which is essentially the, NGS 58, 59, which is, they have a new or replacement for that now. I think NGS 92, their standards and specifications there. Anyways, this is online College of the Canyons, if you're interested. And just going to throw this out there. So in the PDF that I've given you, these links should work. I use this one here more on the datum epic to teach about datum realizations. The difference between the datum realization tag which is in the parentheses, and then the epic date. So that's up there if you're interested. And tonight we're going to cover GPS system overview, GNSS error sources, GNSS because the errors affect other global navigation satellite systems also, and then GNSS survey techniques. So I hope there's something in here. So, I realize it might be basic for some of you that have worked with GPS for quite a number of years, but I hope you find some kind of nugget in here that inspires you to go out and learn a little bit more. So GNSS techniques could be called, GNSS positioning modes, let's say. But this was the title of my course, GNSS survey techniques, that was given to me. So that's what I used. We're going to touch upon point positioning. And there's something called assisted GNSS. Just going to brush upon that. Then we're going to get into differential GNSS and relative GNSS and the difference between the two, and maybe why people confuse the terminology. So RTK, GNSS, and PPK, post-process kinematic. Space-based augmentation systems. And if we have time, a little on network RTK and precise point positioning. Okay, I usually give out, some study resources if you're interested in learning more. There's a folder on the Google Drive that's with handouts, and mostly these are old articles that I think will be of interest. There's some interesting stuff in there, but if you want to learn GPS basics, there's a series of articles that were published in POB magazine, like in the late 90s by Dr. Jim Riley here. And they really cover it good, and you could one article at a time. It's easy reading. The geodesy part that I'm not going to cover tonight, David Doyle retired from NGS. He has a series of videos up. It's on YouTube. This is the Florida Surveying and Mapping Group, Geospatial Users Group. Look for that. You'll find them on YouTube. But there's the videos are about an hour a piece. There's 6 or 7 of them up there. And that's, high quality seminar material, from somebody with 40 years in giving these kind of seminars. So I highly recommend those. And American Association for Geodetic Surveyors has a video series up there. It's in the member section, but student member is only $20, associate member $40. It's well worth it. Online, you can go to gps.gov for some basic information. Navipedia, which is a Wikipedia-like site, produced by the European Space Agency, has a lot of good information in there, technical articles contributed by various scientists. And then if you want to get in depth, GPS for Land Surveyors by Van Sickle. It's up to the 4th edition now, so it's constantly updated. It's got stuff in there on GPS modernization, and the end of every chapter has questions and answers there, so a great study resource. So I use this slide in my map projections class. And this is one of the David Doyle videos. And here's a link to it here. So he covers the difference between conversions, mathematical exact, and then, transformations, which are an estimation. And so we were covering transformations in my class. And we went to this part on Molodensky transformations, which he describes what they are. They're a simplified translation where you take the origin, the center XYZ, and you just move them to coincide, and then apply the ellipsoid. So it's approximate translation, and he describes how some software manufacturers have transformations from built into their software, and they use these Molodensky transformations, which are approximate, and you might get, it might be plus or minus a meter in X, plus or minus a meter in Y, plus or minus a meter in Z. And so anyways, he covered that pretty well, along with the difference between WGS 84 and NAD 83. Don't let anybody tell you they're the same. So, I do recommend this.
I threw those links in the chat. I threw the link in the chat to all of the slides and everything that Steve's already referenced. I threw a link to the YouTube geospatial users group in there, and then also just threw a link to that slide that you're talking about right there as well, Steve. So those are all in the chat.
Okay, great. So I won't go through the video here, but you guys can do that on your own time. American Association of Geodetic Surveyors, surveying. There's 59 videos in here. Let me just see if I opened the window earlier, so let me see if I can share that one. There again, it's in the members section, but you have quite a lot of videos here to choose from. I'd say the bulk of them are done by Professor Charles Gulani. He's authored some books on surveying, so they're all top quality. Just wanted to throw that out there, what you can get. Okay. Also in the handouts, I included this, it's an ebook from Hexagon Novotel that covers a lot of GNSS basics. And then after they sent it to me, they sent me this link they have a series of videos in there too that are all pretty interesting. So that's, I made that available to you. And now with the GPS system overview. So GPS was designed as a 24 Navistar satellite constellation with 3 orbital spares. So 27 satellites essentially. But they've incorporated the spares into the constellation. So it's nominally a 27 satellite constellation. But the satellites last longer than planned. Actually, they have 31 active right now. And they would have more, I believe. There's probably a few more that are parked in orbit that could still work, but they're inactive right now. This is kind of the limit of how many they can control with the operational system right now. Maximum, the P code is 32 weeks long, and Each satellite gets 1 week out of that P code. But with more GPS modernization that's coming, I think they'll be able to control more satellites. And so the satellites are in 6 orbital planes inclined 55 degrees to the equator. And this little NASA graphic was pretty good. I think there's a version of it. So the magenta lines would cover which ones are in view, right? And in one version of this, they have a countdown here, and it'll be 8 or 9, bounces around 7, 8, 9, somewhere in there. And so you notice the Earth is rotating inside this constellation of satellites that are following these 6 orbital planes. 20,350 kilometer altitude, which makes for 12 sidereal hour orbits. Sidereal hour, satellites rise 4 minutes earlier each day. So sidereal day, all the hand waving and words floating in the air, it's probably not going to be enough to describe sidereal day. So you need some graphics for it. So I go where everybody goes, YouTube or wherever I can get some good graphics. But I'll show this one. This one's really short. Some of the other ones I won't get into. So let's see. Let me try sharing that when it pops up here. Let's start that again. No sound to it. So the Earth is rotating as it's orbiting around the sun. So one full orbit of the Earth is about 4 minutes shorter than a full solar day, a little less than 4 minutes. Let's see, we can do that again. So that's the difference between a sidereal day. When it stops, there's a sidereal day right there. And now when it goes and points back towards the sun, there's a solar day. So I look for graphics where I can. Professor Gulani had, I think he had this video and another one in his presentation. 3 segments to the GPS system. The ground control segment that controls the satellites. The space segment consisting of the satellites themselves. And then the user segment. And so notice GPS is a one-way system there. You don't need a radio link or anything to tell the satellites where you are. You're just receiving this data from space, and you're able to determine position from that. And we'll get into that. So the control segment, there's more tracking stations in here than there used to be in the early days of GPS. This master control station, Shriver Air Force Base in Colorado. It used to be called Falcon Air Force Base. You might see that. And now they have a backup control station at Vandenberg and a few more tracking stations around the world. GPS satellite, it's a Block 2A. They're Navistar satellites, navigation satellite, timing and ranging. And they have a couple of different numbers associated with. There's a SVN number or SV number, space vehicle number, which is sequential from when they were launched. I see lately they even refer to the different types of satellites, like the GPS-3 satellites. They have space vehicle number 1 to 10 essentially for the GPS-3. So they've reset that just for GPS-3. And PRN number, that's what part of the code, that 32-week-long P code they're broadcasting on. So right now it'll be 1 to 32, or you probably won't see more than 31. I think they reserve 1 for some kind of testing. So GPS modernization. It starts here on the legacy Block 2A satellites over here. I started surveying when they had the Block 1 satellites up, and you had to go out and sometimes in the middle of the night to get 4 satellites. So this is your legacy GPS. Most of them have this nuclear detonation detection system on them. And then I don't have the years out on here, but that's unfortunate. Then they went to a GPS 2R. And then they some of them were changed to GPS 2RM, were retrofitted. They build them and they'll sit in a warehouse till they're ready for launch. But they retrofitted some of them for a new military signal and a second civilian signal, L2C, and increased jam power. And then it wasn't until they had another contract here to build GPS 2F where they added a third civilian signal, L5. Supposed to have longer life, better clocks in there. And more recently, the GPS 3, I think there's about 6 of them in orbit now. And GPS later in the contract, they're going to put the laser retroreflective array on them, and so on. Now the ground segment here, so it really, if you think about what computers were like in the mid-80s, these mainframe computers, that's what they used to control them for many years. And then they had this architecture evolution plan, because they knew they wanted to modernize, but they couldn't control the modern satellites with the old mainframe system. And so they have a distributed architecture. They have the backup master control station now, and so on. And let's see, OCX, operational control evolution, essentially. So they can control some of the new GPS 3 satellites, but they're not on. They eventually, when they go to this OCX Block 2, they'll have more capabilities. And user segment, of course, this is what we use, and you guys know GPS has evolved to the miniature devices that we can use today. GPS.gov, government, the government site about GPS. So you add these up, you got 31 operational satellites. And they're launching the GPS-3 right now. Currently 6 operational. And so they're taking some of these Block 2 are out. They're taking one out whenever they get a new one on orbit and checked out and operational here. Here's the time frames in here when they're launched. GPS-3 first launched 2018. Block 2F 2010 to 2016. Block 2 and 2R and 2RM 2005 to 2009. Or Block 2R 97 to 2004. And so on. So this diagram shows the 6 orbital planes and where the satellites are parked in this orbit here. This is off of GPS.gov. I believe it's GPS.gov. It might be the Coast Guard Navigation Center here. So these numbers here on the left represent the what longitude the satellite's at when it crosses the equator, when it's the ascending node. So when it's headed north, essentially. And you can see they have some parked right next to each other, so it's like an effective spare. Mostly pretty much 5 satellites in each plane. There might be 1 or 2 with 6 to get to 31 satellites. In my class, we looked at the Coast Guard site to see what's available there.
Go back at the link. The USCG.gov didn't pull up anything. So oh, that one's GPS. Yeah, that one. When you hyperlinked over it, it went to a couple other things, Steve. Oh, Navcen. Okay, there you go. Got it.
Okay.
Thanks, sir. I was trying to search it while you're doing that, but
yeah, no problem. Okay, so now getting into how GPS works. Does anyone want to take that on and give a shot at telling us how GPS works?
the black box for us on this end. And magic from the sky. There you go.
Yeah.
Good job, Brian.
Yeah, it's the voodoo stick.
That's right.
Yeah. Well, I did this in my class. There were a couple of classes before mine that covered some basics and threw this out just so I could find out what they learned. This is a poster off of GPS.gov, and we'll get into some of this. Basics is you need a range to at least 4 satellites, and you're able to trilaterate your position from the known satellite positions and these ranges. Ranges are called pseudo-ranges because there's some errors involved, and we'll get into that. But basically, the range, the distance equals rate times time, and the rate is the speed of light in a vacuum. We do have some atmosphere we have to correct for. And that's sort of the high level view. I know years ago there was a question on the California licensing exam, what are you measuring when you measure with GPS? And I think what they were what they were looking for was ranges to at least 4 satellites. But once you know a little bit more about it, what are you measuring? I think you're measuring, carrier phase angles, actually what you're measuring. And through some sophisticated electrical engineering, you're able to infer that transmit time and infer that distance, or in the survey mode, you're able to calculate the exact number of cycles the carrier phase has come down from the satellite. So nobody wants to try that, huh?
You did a great job right there.
Okay. All right. So basics, I pulled this out of this GPS basics, which I left on there. It's an old handout from Leica. But fundamentally, everything's determined by these atomic clocks in the satellite. You know, see these probably the most accurate clocks you can get based upon atomic clocks, cesium or rubidium oscillators in them, and they're tuned to 10.23 megahertz. That's their fundamental frequency. And so you multiply 10.23 by 154, you get the L1 carrier phase, broadcast at 1575.42 megahertz, which is kind of in the microwave band. And L2 is a multiple of 120, 1227.60. And then modulated onto these carrier waves are some codes, and we'll get that in a little bit. So this CA code, course acquisition code, or civilian acquisition code, 10.23 divided by 10, it's chipped on there at a rate of 1.023 megahertz. And the P code has this 10.23 megahertz out there. And so it's an old slide created before GPS modernization, but the new L5 civilian carrier signal will be 1176.45 megahertz. That's a multiple of 10.23 also. Does everybody know the P code is going away? So yeah, the government's not using it anymore. You know, they've got the M code now. And I believe they have two military frequencies too. We got L1 and L2 and now L5. So I think they have a couple of carrier frequencies they're not telling us about. So they've committed, because there's a lot of, you know, possibly old equipment still in use, is they're not going to get rid of the P code until they have 24 operational satellites broadcasting L5, which is expected to occur in 2027. So looking back here, so L5 is on the block 2F and the block 3, right? So when they get 24, they've got 18. They need 6 more. And what that's going to do is take away these 6. So the block 2R that does not have the L2C code on it. So without P code, you wouldn't be able to track these 6 satellites, right? Unless you wouldn't be able to track P code, because this PY, the P code is kind of how you track the L2 carrier phase. And I'll get into that here in a little bit. But if you're running some old Trimble 4100s or something, it's going to be museum stuff here in a bit. GPS signal structure. So you have the carrier phase. L1 is 19 centimeters, L2 24 centimeter wavelength. And then they modulate on some codes onto the signal, and it simulates a binary code, right? You have, 0 and 1, or on and, or, off and on, essentially, however you do that, 0, 1, 0, 1, and so on. And it's called binary biphase modulation. Some people call it binary shift key. The modernized signals are going to be a little different. They're going to be binary offset carrier. So instead of these 180-degree phase shifts on the carrier, that's how the code is created. These carrier waves are coming in, and boom, all of a sudden there's a 180-degree phase shift. So that goes from 0 to 1 and so on. So this is what it looks like here, 180-degree phase shifts. The new modernized signals, it's called binary offset carrier. They're doing 90-degree phase shifts. Okay, if you see something in here with some decent looking graphics, I didn't create it. This slide I got from Trimble.
Mhm.
But so instead of that two-dimensional location, the carrier wave, it's actually a circular wave coming down here like this. Normally they're right-hand polarized, right? So the carrier wave is coming down, and it's going around through 360 degrees there. And so those 180-degree phase shifts, it's coming around right hand, circling around to the right, and then boop, it starts circling to the left. So this portion of the wavelength, this is, what you're tracking when you first turn it on. And then once you're locked on, you're tracking it from there on. You have the portion of it from when it first locked on, and then you're counting the 360-degree measurements. So here's the beauty of GPS, is the pseudo-random code. You have these really long codes, or a shorter one for the course acquisition code. And you have the one produced in the satellite, and this is modulated onto the signal. So that signal's coming down with this code on it. Then the receiver is producing an identical code, right? And you have to, and there's some delay, right, before from when the signal left the satellite to when it's received. So you'd have to shift the receiver generated signal back to match up the satellite generated signal. And you're getting them matched up. And when they align here, then you're locked onto the satellite. You're locked onto that signal. And this is how you're able to track a signal that's like, it's very weak signal. It's not louder than background noise coming from space. It's said to be like a 40-watt light bulb 20,000 kilometers away. And but this is how they get to track that signal, to lock on, is this PRN codes. Now they're called pseudo ranges because you have the measured range, and then there'll be a clock error. So you don't have a calibrated atomic clock in your receiver. It's, a cheap quartz oscillator. So there'll be a clock error, and then you have the the atmosphere that it goes through. That throws an error in there too. So the pseudo range, basically speed of light times the transmit time equals distance. So you're shifting this receiver generated signal back, and that amount, that's the travel time of the signal. Right, so that's your transmit time right there. And I threw this in here. Dr. James Riley here, he covered that very well in the series of articles. And so while it's late 90s, still gives you how GPS essentially works, but without the modernization part. So were there any questions so far?
So far, so good.
Okay.
Unless anybody wants to jump in real quick. How does a receiver store the replica code?
Store it? Well, that's a good question. It
The almanac, he says.
Should be predetermined. It's a 32-week long code there, and it's a known, so it's part of the firmware, right? The almanac is where the satellites are. That gives you the quote fixed position. So here's some errors involved on that affect that signal coming down from the satellites. You have the clock error in the receiver. Remember, that's like an inexpensive quartz oscillator there. Satellite clock error. These are the best clocks you can make, and even though then they have a little bit of drift. They have to be managed. A little bit of drift, a little bit of offset. So that's part of the transmit, the encoded signal. The satellite orbit error. How close is that orbit that's the satellite is transmitting? It would be a predicted orbit. And then ionospheric delay. This is the biggest one here. I'll show that in a bit. And then the tropospheric delay, neutral atmospheric delay. You got wet and dry portions to that. Satellite geometry can have an effect where the satellites are in the sky. And multipath, that's like it sounds. You get multiple signal paths into the antenna. And then receiver noise, which is noise from internal electronics or the cabling. A lot of times it's kind of used as a nuisance parameter too, to throw in unmodeled error into that receiver noise. So I showed this in my class. I don't think I'm going to show this one here, but satellites are orbiting 20,000 kilometers up and moving pretty fast. So special and general relativity affects the time there, and it affects the clocks there. So those atomic clocks have to be calibrated on the ground, pre-calibrated for what these effects are going to be. And these guys are flight instructors that did this video teaching their students about GPS, and I think they thought this was pretty cool. But The satellites are pre-calibrated to correct for this. And what you have left is residual, drift and offset errors. GPS signal delays. So ionospheric is, upper atmosphere there. I think it's up to 400 kilometers. So it's dispersive, so it affects different frequencies differently. So it's inversely proportional to the square of the frequency. And so by measuring on two different frequencies, we can remove most of this ionospheric error. And now, so ionosphere is it's a layer of charged particles. And, when you get a solar flare or something, it really excites these particles. So keeping an eye on the solar weather is a good idea, a good practice for when you're going to go out and survey. High ionospheric activity, it could pull on that signal like a rubber band, and it could stretch that rubber band so fast it'll exceed the tracking bandwidth of the phase lock loop there on the receiver, and you get a cycle slip, right? So cycle slip, then you have to start all over again, figure out what the integer ambiguities are, and we're getting to that. So troposphere, weather could affect this. And actually they're actually using GPS now, these permanent GPS stations, they're able to predict severe weather events by measuring the water vapor in this signal path. They're inferring it out of permanent GPS there. So ionosphere related, you have the total electron content will affect the signal. Ionospheric effects will be greater on the equator, and then in the northern latitudes, milder in the mid latitudes. So you have the wet delay integrated, something or other water vapor in here. So this is a page out of that hexagon Novotel book, or a couple of diagrams out of there actually. And I like this because they give you an approximate error. They put a number to the, how much error could each one of these affect that signal coming down from the satellite. Multipath, maybe a meter. Orbit errors, 2.5 meters. Ionosphere here is the biggest one, plus or minus 5 meters. In troposphere, much smaller, 0.5 meter, and so on. So International GNSS Service, they produce the precise ephemeris. And if you're going to do high accuracy work, you're going to rely on the final precise orbits are available 2 weeks, approximately 2 weeks after survey, or they have rapid orbits, maybe about 48 hours after. But here they say broadcast orbits, about a meter accuracy, and then the accuracy of the clocks here, 2.5 nanoseconds standard deviation, 5 nanoseconds RMS. And you get down to the final orbits here, about 2.5 centimeter positional accuracy, and standard deviation of 20 picoseconds here. So this is much better. Trent mentioned I've been doing GPS on benchmarks, so they'll only accept the rapid or the final in here. So I wait the 48 hours and then I submit, I get an answer. I don't wait the 14 days because NGS is going to reprocess them anyways later on with the final orbits. Anyways, IGS site, they have a lot of good information on there. You can look at that. So positional dilution of precision, which can be broken down into horizontal and vertical dilution of precision. Usually a receiver will give you a number here and a dot value. So this is a measure of the geometry. So one or less than one is ideal. 1 to 2 is excellent geometry. 2 to 5 is good. 5 to 10, maybe you don't want to be out surveying during that, or observe through that moderate area. And really large numbers, probably avoid those altogether. So some more Trimble diagrams here. So good positional dilution of precision. You want satellites in all corners of the sky. I would also add, you want one above you too, right? You want the best geometry you can get. This is PDOP. Now with GPS, vertical is always going to be worse, for one, because of the geometry. You don't have any satellites below the antenna, coming. You don't have any signal coming through the earth to give you good geometry above and below. Bad PDOP, all your satellites are parked in the same area of the sky. So with 31 operational GPS satellites plus other constellations, this isn't so much of a problem anymore.
I was just on that note, the burning question, is too many satellites a problem?
Yeah, I would say no.
Okay. All right.
Not for post-processing.
For RTK.
Yeah, RTK, maybe, because you've got, so GPS and GLONASS, they have different reference systems, different clocks. It might make it slightly worse, but what I found is it makes the difference between getting a solution when you're in a valley or with some high rises down the street. It makes a big difference. But post process, where everything's, they're post computed orbits and clock corrections, I would say no.
Yeah, for sure.
So this diagram is kind of showing you that for lines less than 10 kilometers, you're essentially going through the same atmosphere, ionosphere, and troposphere. And so those errors will cancel out when you're doing relative positioning here. But for longer lines, you're over 10 kilometers out, 20, 30 kilometers or more. You really need to do some kind of modeling to help reduce that ionosphere and troposphere error. You definitely want dual frequency data here longer than 10 kilometers. Shorter than 10 kilometers, you can get away with it. Most of the time, I would say. Shorter than 5 kilometers, is probably most of the times. Little tremble sound effect there. Then you have a signal multipath, which is just what it says. You have another signal reflected off of some surface that's making it into the antenna, right? And they have ground planes to kind of minimize this, and they do some filtering now, but it's really hard to get rid of. It's what they call an attenuated signal. And why do we have a ghost in here? Is there anybody old enough to remember television with the antenna on the roof? Yagi antenna. You remember, you get a station far away, you kind of get a ghosted signal coming in and out. Well, that's multipath, right? You've got two different signals coming in. It's a ghosted signal. And so here it shows you the amplitude as a function of this incidence angle. So antenna phase center models. So this wasn't known back in 1990, 91 when we did the HPGN survey. But different antennas act differently. They have a different electrical phase center, right? And the phase center moves around with the angle of the satellite coming in. So just an aside, we were doing the getting ready for the HPGN survey in California, 1990. And we were planning on mixing Trimble antennas in there with Ashtec stuff. And San Diego County, we had 34 receivers going at one time. So we thought ahead of time, we thought we'd do an experiment, well, how are these going to work together? So we had Dr. Bach at Scripps come out, and we had two Ashtecs, two Trimbles. And at the county here, we just set up a little square up at the Miramar landfill, about 100 feet square, 4 points. And we leveled between these marks. We measured the HI to 3 different places around the ground plane. We checked it with our pocket tape, measured before, we measured after. And then, we also leveled to the tribrac. So we pretty much knew there was no, we didn't have the HIs wrong. But anyways, a couple months go by, we get a call from Dr. Bach there, and says, you guys must have messed up on the antenna measure ups. No, here's all we did. We checked it, 2, 3, 4 different ways, and our measure ups are right. Well, it must have been the deflection of the vertical then. And that didn't quite sit right by me, because we're only 100 feet away from each other. The deflection of the vertical doesn't change that much. But come to find out, it's antenna phase center models. It made a couple of centimeters of difference there, mixing Trimble and Ashtec. Now, once you use those models, that's all calculated out. Anyways, antenna phase center models. Different antennas have different phase center patterns. Kind of getting towards the hour, right?
Yeah, you're doing good. But I don't know how many more slides I have left. But
well, I threw 2 in. I had 70 slides or so. So that's way too much.
Yeah, there you go. Well,
now we're just getting into GNSS survey techniques here.
Whenever you get to a breaking point, we can always come back for part 2.
Okay.
So
I'm good for maybe another half hour at the most.
yeah, no, you're totally fine. You're totally fine.
Okay.
So whenever you want to cut it off, like I said, we'll do a part two.
Yeah.
Then.
Point positioning. Okay.
All right.
Point positioning, that's the, 4 ranges, ranges to at least 4 satellites. And you get 4 equations and 4 unknowns, 3 unknowns being the XYZ of your receiver location, and the 4th being the receiver clock error there. So that's why you need at least 4 to calculate a position. So here's a video I'd recommend if you really want to learn, how the the how the system determines the transmit time from the broadcast pseudo-random noise codes. This is one of the AAGS videos. Thomas Meyer, I believe he teaches University of Connecticut. Covers it really well. It's 43 minutes long, and even at that, he kind of says, well, in a couple places, it's a little more complicated, but here's basically how it works. So there's a lot to it. And these are some old slides. So before May of 2000, GPS was performing better than the Department of Defense really anticipated. So they didn't want to have somebody use our GPS system to guide a missile in on us. So they dithered with the satellite clocks to purposely degrade the signal to 100-meter accuracy. And then Bill Clinton ended selective availability in May of 2000. Probably it was getting obsolete anyways with the D GPS beacons. That was countering the effect of selective availability. So it was a little bit obsolete anyways. And there's speculation on other reasons for that too. So here's what's called code phase. You're just using those PRN codes to determine the position. And this is differential correction. So this is using what used to be a Coast Guard beacon. And I'll cover that in a little bit. So a basic correction, you're down to 1 to 3 meter accuracy, and vertical's worse, 2 to 5. So here it says you can post-process or FAA and USC and GS. So the Coast Guard beacons they've been decommissioned, and the FAA has wide area augmentation system now that we'll cover in a little bit, that which is much better than the simple differential correction. So future corrections, these are old slides. So I think we're pretty much here already, 1 to 3 meter, you're getting a position. Some manufacturers will tell you, oh, we're getting better than a meter. Here's the assisted GNSS or assisted GPS. I said I was just going to brush on. So in the early days of GPS, it could take up to 20 minutes for the receiver to download an ephemeris, the satellite orbits, to tell where the satellites are before it could calculate a position. If you hadn't turned that receiver on in a week, it wasn't going to display a position for 20 minutes or so. So that wasn't the 911 folks. They wanted cell phones they want cell phone location. You know, they waiting 20 minutes on an emergency call is not good enough. So what assisted GPS is you're getting the satellite ephemeris or orbit data through the cell network, you know, shortly after you turn your cell phone on, so it's able to calculate a position right away. And I believe I saw on the NASA JPL website, I think they produce some of those orbits, so they're probably better than the broadcast orbits. Now, this was differential GPS. So you have, you know, a rover out here, and you're doing a point position solution, but you're also listening to a radio broadcast that's broadcasting the difference between a point position solution over a known point and the known good coordinates, right? So at this point in time, there's you know, the point position solution is 50 meters in a certain direction, and it's broadcasting that correction over here to the rover, and it's applying this essentially simplified correction. And these were radio broadcasts, usually along the coast by the Coast Guard for navigation purposes. And so these have all been decommissioned. This is Wikipedia here. I say all. The US and Canada have decommissioned theirs. There may be some others in the use around the world. And then quickly, satellite-based augmentation system. This is where you have a geosynchronous satellite transmitting corrections, probably better than the DGPS. It's transmitting corrections on, and it's all on a L-band frequency, and it's assigned a pseudo-random code number here. So you have 1 to 63 are assigned for GPS, 64 to 119 for ground-based augmentation systems, and then 120 to 158 for satellite-based augmentation systems. And so the US has WAAS, Wide Area Augmentation System, from the FAA. There's 3 geosynchronous satellites that broadcast that. Europe has this IGNOS. Probably is going to be 3 of those too. There's 3. And, you know, Japan has this MSAS, and Russia SDCM, and so on. But not only you're getting corrections on an L-band signal, it's also transmitting, most of them are transmitting a GPS-like signal too. So you're getting ranging from a satellite that's basically parked. It's parked over the equator. So if you're up in Alaska, you may have trouble seeing some of these geosynchronous satellites, but mid-latitudes, it should be, you know, fairly high in the sky. So you're getting an extra satellite signal, and then you're getting corrections. So including satellite orbits, clocks, and atmospheric delays. And then the big function of WAAS is an integrity channel. So it'll broadcast some information on the health of the satellites as monitored by an FAA network of tracking systems. This link here is a little video from the FAA on how WAAS works. I don't think there's any sound to it. And here's the 3 geostationary Earth orbit satellites for the US supporting WAAS. So now finally getting in survey grade here. And this is a photo of one of my former party chiefs at East Bay Mud. And the McCallum River there in the background, water supply for the East Bay. So up to now, we've been talking about, GPS is what it was designed for as a navigation system. And so it was determining a position based upon those codes. It was codes-based navigation. It wasn't until Ben Raimondi in his 1984 PhD thesis that it became survey grade, essentially. He developed the foundation for essentially differencing. And notice it says relative geodesy in here. I'm going to get into that. So differencing satellites to get more accurate ranges to the satellites by several orders of magnitude, by tracking that carrier phase, by calculating the number of waves that have come down from the satellite to when it was received in your receiver. And he also pretty much invented RTK too here in the early 90s. I believe when he was working at Ashtec with the group there. This article mentions a few other people. There's a link in here to the American Surveyor, to their article. So the key to survey grade GPS is counting the number of cycles that have come down from the satellite. Well, not counting. What you're counting is from when you turn it on, you're counting the little portion of phase and then the number of cycles that have come down afterwards. What you don't know is the number of cycles that have come down before you turn the receiver on, right? So this is what you need to solve for, is this integer ambiguity. This is how you get down to centimeter level precision. And at centimeter, it's relative position, because you're computing a vector. You're determining the position at one point relative to another. A vector has distance and direction here. So relative positioning uses double differencing, solves for the energy ambiguity, and computes a vector. This is survey grade here. And double differencing, so let's go to the next slide. Single differencing is the difference. You're differencing the signal from one satellite received at two stations. And then double differencing is you're taking two of these single differencing at the same epoch and differencing those. And that's how you can solve for that energy ambiguity. Now, they used to do triple differencing, which is the difference of two double differences at consecutive epochs. But, the algorithms have gotten much better now that that's not used so much anymore. So the triple differencing, the ambiguity goes away. It would come up with a solution and then hand that back to the double differencing solution. So you had a smaller search area to search for the ambiguities. And Professor Galani here covers that pretty well. This is the time in the video that I showed my class. So there again, you're measuring a vector. This is relative positioning, the Trimble slide. And RTK, you're doing that relative positioning in real time. So you set up over a known point, you've got a radio, and you're broadcasting out. So you're receiving the same signal at the base and the rover. The base is transmitting the data it received, and then the rover is calculating this vector here. So real-time kinematic survey. Now these slides, they're a little bit old. I think they had a 2004 date on them. But so how do you get from, you used to have to observe for an hour or more to resolve all the ambiguities, and then all of a sudden you can do it now in minutes with RTK. Well, they had this on-the-fly initialization, and I believe what that is you have you're narrowing down that search window for ambiguity. So instead of the software trying to figure out where you are in all of space, you start with your best estimate there from the code phase solution. And within the error volume of that, you start searching ambiguities in there. And so what does it take to initialize now? Less than a minute. Pretty amazing. But here in 2004, maybe it wasn't quite so good. You had to rove until you got to a fixed solution. Took a few minutes. You need at least 5 satellites to do on-the-fly initialization. So you're going around and you lose lock. You have to go back to a known point, pick up your ambiguities, and then continue on with your survey. You end up with a radial survey. I threw this in there for my class. I won't go into this much, but so this is from Navipedia, scholarly articles. I just wanted to throw out. So Opus would use an ionosphere-free combination, which is just a linear combination. You could have L1, L2, or now with L5, that opens up some additional combinations. But this removes the ionospheric delay here. Ionospheric effect is inversely proportional to the square of the frequency. So the square of the measured phase on L1 minus the square of the measured phase on L2 over the frequency of L1 squared minus frequency of L2 squared, and similar thing on pseudo-range. So then there's, you might hear wide lane thrown out there. And so this is another linear combination. It doesn't have the squaring in there, but it has a wider observable 86 centimeters, let's say. So that's easier to fix an ambiguity than the 19 centimeters of L1. And so you can fix the wide lane solution and then hand that back off to reduce the search area for the L1 ambiguities. And narrow lane, so lower noise ratio, different combinations. So frequency, L1 plus L2 instead of L1 minus L2. And here again, off of Navipedia, shows the wide lane using L1 and L2, 86 centimeters wide, L1 and L5, 75 centimeters. L2 and L5, 5.861 meters, and so on. All right, PPK.
That's probably a good spot to stop, since you kind of got to a new topic.
Okay.
If you want. Unless your PPK is fairly quick, but your call.
Yeah, PPK, same as post-processing, except for might be some advantages here. That's used for UAVs mostly, because you don't have to put the weight of a UAV on the vehicle, and then you don't have to worry about losing signal during the flight. And there's some advantages. You can use a precise ephemeris, or you run it forwards and then backwards in time and check for discontinuity. So that was my PPK rant there.
Actually, you only have 8 more slides. Might as well wrap it up.
Okay.
I just looked. I just saw your thing. I'm like, oh, you're almost done.
Yeah.
Perfect.
Yeah, these are old slides from NGS 2. So RTK today, about 2 centimeter accuracy. And you can go maybe as far as 10 kilometers from your base station. Here with a tractor, I would say most contractors would put a base station on site, because you'd carry a better vertical there than you would from a base station 10 kilometers away. But here they're saying, you know, with the new codes, you get the same accuracy. You can just go farther from your base station. Construction site, I would still put a base station on site. And network RTK, what this is, by having a network of base stations reasonably close, within maybe 30, 40 kilometers, you can do some modeling of the, ionosphere and troposphere. And I believe they also apply some clock corrections too. They could be giving you solid Earth tides and ocean tidal loading and that kind of corrections too. So what this is, if you're, I wouldn't use this if you're under, let's say 8 kilometers or so, 5-8 kilometers. Not necessarily necessary, but it allows you to fix those ambiguities at a longer range, out to 30 kilometers and stuff. And so the reason why I wouldn't use it on the shorter lines is because there is some modeling involved, but it does help you get the right numbers the farther away from the base station you are. I did include one paper on the max auxiliary concept. It's written by somebody working for Leica. So it's different than the VRS, but it's an open system, and others use it too. That's why I've got the SmartNet link rather than the Trimble link here for the VRS diagram. And then last, precise point positioning. And this is really getting approaching even survey grade now. So invented by Natural Resources Canada for years ago for positioning out in the outback. So you don't need a base station. It relies on, precise orbits and clock corrections and the other corrections like the solid Earth tides and all. And even satellite windup corrections too, and that's a whole nother thing. But so it used to be, Trimble would have like this exfil they're running the PPP in the background, and when you lose your radio signal from the base station, the PPP takes over, and it carries the solution for up to 10 minutes. They had some drift to it. So that's why they limit it to 10 minutes. But now they have a newer version that unlimited that really keeps that accuracy. I'd like to know a little bit more about how they're doing it. Um, so, anyways, I got this off the internet. Here down on the bottom, notice they say differential processing. That's where they're getting the terminology wrong. This is relative positioning that they're talking about. So you can look at Navipedia, Natural Resources Canada. You could submit a file to them. I have my students do that. And, it's really pretty comparable to Opus. I think there was a little bit of bias in the reference systems, but still an excellent solution. It used to be when it first started, it would take 20 to maybe 45 minutes for it to converge to get down to, decimeter level or better, or around decimeter level. Now they're getting ambiguity resolution out of precise point positioning. And I think you're on the order of about 1/10 of a foot or so horizontally and maybe 2/10 vertically. JPL had something similar. I actually couldn't get this to work. Either maybe they don't have enough computer resources to handle all the submissions, or they've taken it offline. And here's the Trimble link to the Trimble website. Centerpoint RTX is the top of the line, and I think it's Ultimate is the higher cost service that does not drift. And of course, Leica has something similar. And so that's all I got.
First off, that was far from the basics. That was awesome though. Yeah, Brian, very detailed presentation. Exactly. One question back to the PPP. Do you need internet connection to do PPP? For example, offline in the brush. It's like Opus, correct?
Well, if you're using the Trimble RTX, the answer is no, because you can get it through the internet, or you can get it via L-band straight from that geostationary satellite. So they have two ways to get the correction.
Okay, got it. You got to go to your last page of your slide. Go all the way to the end because it's got your. There you go.
Okay,
I love that one.
that's me. Yeah,
that's you. The Caltrans survey buses. I love it. That was a good one.
I got that from Vance Brashears.
No, that's very cool. Does anyone? There's so much to digest there, but anybody have questions they want to ask or unmute or type in the chat and I can ask?
Yeah, I was wondering, do you have any good books for the post-processing portion? When you're doing like control for a project, to get you a better understanding what the least squares is doing and the Rhinex data, because every other example is business related and it doesn't really pertain to surveyors too much. I'm looking more survey based.
Nice.
A book for that, besides the GPS for land surveyors. I don't have a good book, but there's, recommend the College of the Canyons online program there where they cover that. Kevin Maxwell will be covering, he uses Trimble Business Center. So that's coming up. I think maybe it's this week. I'm not sure when. It might be starting tonight.
I will also see if I can find somebody, Dan. and see what we can do on that too. Try to at least do a quick one on that. But yeah, I agree. All the books are more on the academic side and not really down to the nuts and bolts side of it. So
Yeah, you know, I've never been a Trimble user, so you know, I couldn't teach a Trimble Business Center. And you know, the last 15 years or so, I've been a supervisor, so I haven't been, you know, the guy pushing the buttons for a while. You know, I'm
yep.
still able to kind of help do some troubleshooting, but as far as how to use the software, um, you know, I think Kevin Maxwell will be better at that than I.
Okay. We'll see what we can do. Anything else you want to add to that, Dan? I saw you unmute there. So
Oh, no, I just,
okay.
I would just get nervous as there's a lot of people who do post-processing, and they're just taking what the box says and nobody fully understands what's going on. So
Right.
I always tell them I'd hate to go to court and say, or how'd you come up with your accuracies or whatever, you know? And I'd say, well, that's what the computer told me.
Yeah.
That's kind of scary.
Well, I used to include a part on GPS standards and specifications that covers some of the procedures. You know, you only want to use the non-trivial lines, which if you got 3 receivers going, there's only 2 non-trivial lines. I mean, the software will calculate 3, but one of them is like just an inverse. It's like a perfect closure. So there's only 2 statistically independent lines with 3 receivers going at the same time. So that's a concept you need to learn for control work.
Yeah, there seems to be a lot more ideas out. Dan Gillens has got like a hybrid. There's a paper written by him and Weaver back in 18, I think. But everything seems to be so old that I don't know what to do now with, you know, I think I watched one of these videos in 21. I can't remember what week it was. Dave Doyle's on here.
Yep.
At the time, he said that L5 is not being used. Is L5 and L2C being used right now? Can we use that in our solutions, RTK?
Yeah, I would say yeah. You know,
Okay, that's what I thought. I just was, you know, you read one thing and then doesn't make any sense, and you're trying to put together on your own, and
yeah.
sometimes you just guess and hope it's right.
Exactly.
Yeah, let me chime in there. On the L5 thing, the issue at the time was you have to have so many satellites that have that capability before they could fully test and prove the reliability of that signal. So I don't know where we are in that process. It would be interesting to find out. The other thing, I'm going to go back to something you were asking about regarding processing. I was messing around with, well, full disclosure, I I do seminars too. I just retired from teaching surveying for 25 years at Parkland College in Champaign, Illinois.
Oh, fun.
And I've uh, done some training on relative positional precision, and especially when it comes to combining GPS and optical networks, this this became real critical for me to understand, and that is sometimes you have to degrade the data on your GPS vectors significantly because the data is notoriously optimistic on their covariance matrices for your 3D vectors. So when you are starting to combine surface measurements, optical measurements with GPS measurements, the GPS measurements can skew your network adjustment to the point where, well, long story short, it can make it look like you're creating precision out of thin air. That is, you start ending up with greater precision than your original control, which, you know, that defies the laws of physics right there. So I learned this not from a textbook, because yes, most of them out there are highly academic and not written for humans. But I got a great deal of value from the tutorial files that come with StarNet, Microsurvey StarNet, and I was also using Carlson's ServNet. I was actually using both of them side by side, and I can't remember which one showed this, but it basically said, you know, you got to take those GPS vectors and you got to put this multiplier on them. And I had to play with it, but I found that usually between a multiplier of 6 and 8, it would basically amplify the error estimates to keep my results from being goofy. That is, creating precision out of thin air.
Well, I'll agree with that. GPS, the error estimates were known to be at least 3 times
Yeah.
more optimistic. As far as scaling, you know, I think some vendors will tell you to, you know, scale your network so that the standard error of unit weight will come out to 1. You know, do your minimally constrained and scale it so everything equals 1, and then constrain it. I don't necessarily agree with that. That's having your statistics tell you you're perfect every time.
Mm-hmm.
You
Mm-hmm.
know, I would come up with some empirical value if by your experience using your equipment and the procedure you used, it takes a factor of 6 to 8, you know, to make that difference. I would hold that 6 to 8 for every survey and not scale it different for each one.
Right. Yeah.
Good stuff, Todd.
Yeah, thanks. Well, the stuff that Dan was asking about
Yeah.
got me
No, I love it.
thinking about that.
No, I love it. Yeah. Good stuff. Anybody else? No, Steve's probably got to start making dinner, so.
The wife isn't even home yet.
Just one more thing.
Yeah,
you
go
talked
for it.
about the American Society of that ags.org.
Yep. AAGS. Yep.
If I was a member of that for a year, I watched all those videos, but it seems there's nothing goes on there. It's just nothing really happens on that group. Am I missing something? Or because they were talking about doing a certification for a geodetic surveyor, and I haven't heard anything on that. So
Right. They're still working on that. I think that's coming up. So I'm just new to that myself, but Scott Martin here in California, he's with Caltrans, and I think he's going to be the incoming president. So he talks about that, and I think that's coming. So there's still stuff coming. It's a relatively small group, so it's all volunteer effort, but I think they provide a good value there.
Yep. Agreed. I'm a member as well, and it's like you say, it's just a smaller group trying to do a lot with very few bodies. So
yeah.
Rosalie had a question in the chat. You want to ask it, or is that something else too? She had a thing in the chat too. I'll let you ask.
Yeah, it's pretty quick. Sorry for this late, but I have a G07, and I was taught how to use it by watching my previous the person that used to handle it. So all I know is that my delusion of precision cannot go way beyond 5, and I'm green on knowing how can I describe my GO7 with with its rover and dome? As what type of GPS is that? Is that a network RTK? Or am I giving enough information for it?
Well, I'm not familiar with the GO7.
It gives centimeter precision.
Well, that's now if they're talking about centimeter precision, that would be RTK, right?
Mhm.
I know there's you, if you go to the ESRI conference, you'll see all kinds of vendors there, and there's EOS Aero GPS, which is a little tiny little cell phone size box and an antenna on a stick, and well, that's getting RTK now too, which is centimeter level relative to positioning. So it's relative to a base somewhere. And if you only have the one, is there a cell phone or a cell connection? You have to have connection in there.
For the one that I'm using,
Yeah,
um, yeah, internet.
you have to have internet connection. So it's probably getting a correction over the internet from
And
a
when
base.
oh, sorry, go ahead.
Um, yeah, from a base somewhere. If they're telling you centimeter level, that should be RTK.
Hmm.
You did throw me off a little bit when you said the PDOP can't go over 5, let's say, because that would be a point positioning solution. Although it does affect RTK too. So um, centimeter level, it should be RTK.
Okay, thank you so much.
I just threw I was looking at it while she was talking about it. It is one of the handheld ones. Steve, I threw in the chat the link to it on the I
Okay,
was just trying to thumb through it really quick, but
yeah. So it's probably connecting to a Trimble network somehow.
Yes, and I have a couple of bases nearby, and I can use it to generate differential correction. Um, of course, after after 24 hours, I usually do that. I don't need too much precision for the type of work that I do. So
Yeah.
that,
Right. There again, that's terminology. You said differential correction, but if it's RTK, I was taught, survey grade is relative, but there's a whole generation of folks out there using differential for survey grade also.
hmm.
perfect.
All right.
Anybody else? That was great, Steve. I loved it. Thank you, sir. Again,
Okay.
way above the basics, but I love it.
Uh,
Thank you for your time.
well, okay.
That's good. I love it.
All
All
right. Well,
right. If anybody has anything else, Roundtable Tuesdays is tomorrow night. If anybody wants to jump on that, it's mental health with Adrian and then Peter Cox from Australia as well. So got a couple of things going on this week. So and then Wisdom Wednesdays is back next week. So any of those you can certainly catch up on. But I love it. As always, have a good week, everybody. Thank you, Steve.
all right. Thanks for having me on.
Of course. Bye, everybody.
Good night.
See ya.